Good afternoon, ladies and gentlemen. My name is Ilya, and today I'm going to present to you our work, Tensor Ensemble learning, which me and my colleagues Ahmad Maneri and Professor Daniel Matic have been conducted at Imperial College London. The outline for my talk is as follows. Firstly, I'm just going to touch upon the concept of wisdom of the crowd, how we as a people come up with collaborative solutions. Then we will just see how these basic ideas have been employed in machine learning. Then we will slightly touch on the somewhat novel way of representing data with keeping the original structure, and which will be initially followed by the introduction of some basics for tensor decomposition. Then I will introduce to you our framework which we proposed in this work, and finally I will conclude with some simulations and results. Okay, so I'm sure all of you would definitely recognize all these images straight away. Yes, it is from the very well-known program Who Wants to Be a Millionaire. So when the participant would get stuck at some particular question, he would have three options, but two of those are of particular interest to us. First is a call a friend, and another one I'll ask the audience. And one of the very fascinating facts about these, whenever the participant would choose to ask the audience would get the correct answer almost all the time. Even though they're not, none of them would be experts in the particular question. Whereas with a friend, it is more like a game. These basic concepts have been employed in machine learning, and this framework is called ensemble learning. So essentially what it does, it just employs multiple base classifiers which are trained on the same data or on the same versions of data, and then each of those base classifiers, they come up with a different hypothesis about the data, and at the end their decisions, they just combined in order to produce the final result. One of the strong assumptions for this framework to work is that the individual errors made by the base learners should be uncorrelated. But before we go into that, I just want to tell you about three base frameworks within ensemble learning. So first is bagging or bootstrap aggregating, and it does what it says. It subsamples data, the original data with the replacement, and after that employs multiple classifiers which are trained on those subsampled version of the data, and therefore the final hypothesis to separate one class from another or would be slightly different from each other. Next is a stacking, and essentially over here again the same multiple classifiers are employed, but there is additional layer at the learning process called, which is sometimes referred to as blending or meta learning, and the main purpose is to combine the outputs of those decisions in a more probabilistic way to come up with a final hypothesis. And last major framework is boosting, and the main idea is to pay more attention to the errors at the testing stage, at the training stage, and therefore the model would pay more attention to those particular samples and would assign slightly different weights, and in that way the final hypothesis would be more adjusted to produce the better result. So we wanted to employ this framework and to unify it with multidimensional representation of data. And the units of such data are tensors or multidimensional arrays, which is a generalization of the matrices. Tensors, they're mainly composed of some basic elements, and in this example we just refer to the tensors of order 3, meaning that there are only 3 dimensions, because it is very easy to visualize. You can slice and dice your n-dimensional array with and you would come up with some matrices forms. You would take vectors or two fibers, row vectors, column vectors. You can manipulate with all these data. You can reshape it in any way, pretty much in any way you want, as long as it makes sense. And you will get, again, slightly different representation of the original data. So when do we encounter multidimensional data in real life? when we watch a video, which is essentially a sequence of just color images, we can stack all those images on the third dimension. Here is your multidimensional array. We can represent image in natural colors such as red, green, blue, and again we would come up with a three-dimensional array of data. If we perform, for example, EEG recording of your brain activity, and after that, for each time series, we can employ Fourier transform to represent the time series in time frequency domain, and then we can stack all that information together in order to obtain multidimensional arrays. Then the next step, once you have multidimensional data, you have new opportunities, new decompositions, which are specifically applicable to these sorts of data. In our work, we focused more on Tucker decomposition, which essentially represents your original data in the form of some core tensor and some factor matrices. These factor matrices, in general, they're not unique, but what is unique is the subspace that each of those define, and due to the fact how these factor matrices are obtained, which I'm going to come to on the next slide, these subspaces, they are as uncorrelated as possible. So as far as computation of Howard single value decomposition, which is just only a particular case of Tucker decomposition, as far as computation is concerned, so first what you would need to do, you would need to unfold your original data along one mode, perform singular value decomposition in order to extract first factor matrix, repeat this process to obtain all other factor matrices, and at the final step, all you would need to do is just to compute the core tensor for this decomposition. So now I'm just going to tell you how we try to employ and unify both of these two frameworks, multidimensional representation of data with corresponding decompositions and ensemble learning together. So whenever you would have a trained set of naturally multidimensional samples of data, what you can do, you can perform a particular tensor decomposition on each of the, so you're given training data, you perform tensor decomposition on each of the samples from the training data. After that, you would regroup the components that you've obtained from this decomposition, and therefore you would get some n number of train sets. Therefore, you can employ n classifiers, n base learners, which can be then trained separately, and in the end, you would need to just combine the decisions for the new unknown sample in order to identify the label if it is a classification problem, or to formalize the final value if it is a regression problem. So now I'm just going to give you a more illustrative example of how our framework works. For the simplicity's sake, we consider the very intuitive example of a red-green representation of color image. After that, after we would perform the Howard single value decomposition and represent it as a outer product of these base factors and their linear combination, then what we can do, we can separate all of these different elements, all of these factor vectors in separate train sets. So 1, 2, and so on and so on and so on, depending on the particular case of your tensor decomposition. And you perform it for the new sample, you append it to your existing train sets, and you do it for all of the samples in your train set. Then it is a train stage where you use those obtained train sets and you train a particular machine learning algorithm such as support vector machine, k-nearest neighbors, or any other. And again, all these algorithms, they are getting trained separately from each other. After you would obtain trained base learners and the new unknown sample came, which you decomposed with the same type of decomposition on which these base learners were trained, the only one thing left to do is to classify separately each of these factor vectors, and these base learners would provide the corresponding label if it is a, again, classification problem, and you can go one step further. You can get a probability distribution for the possible classes. And the most simplistic way to combine the outcomes of these base learners is just by aggregating the probability distributions, because it is more robust than just doing majority votes on labels. You would combine it, and even if over here one of the base learners was pretty confident that this sample is an apple, another one would be pretty certain that it's not, but in the end the chances are they would come up to the final solution again by the virtue of the wisdom of the crowd or a mixture of learners. So we've evaluated our model, our framework on the ETH80 dataset, which consists of 8 different categories, some of which look very much alike, like over here, with horses, dogs, and cows, or apples and tomatoes. Each of these 8 categories contains 10 different objects, and for each object there are 41 images taken from various angles. And all of it totals in 3,280 samples. So first we evaluated our model in order to see whether it performs as the classical ensemble learning, meaning that the weak estimators, after their decision are combined together, they would provide you with increased performance. And this is what we see on these graphs. None of these base classifiers which were trained on a particular factor vector of the matrix exceeded 80% on the accuracy score on the testing data, but after we've combined all of them, the result was almost 95%. Next, we compared our proposed method to the closest framework within classical ensemble learning, namely Bagging classifier. And as we can see over here, even though sometimes Bagging classifier was not able to provide you with the desired enhanced performance, our proposed framework still was capable of improving the final result. It's also worth to mention that all Bagging classifier in our framework, they were employing the same number of base learners, they were trained on the same type of training data, and they were tested on the same type of tested data. And all these results were obtained by averaging across 50 different runs of the simulation. So, in conclusion, we proposed a new framework, namely Tensor Ensemble learning, as a means for generating ensembles of base estimators for multidimensional data. Tensor Ensemble learning is highly parallelizable due to how base learners are independent from each other, and therefore is suitable for large-scale problems. And the enhanced performance of the proposed framework in this case was due to the employed tensor decomposition, high-order singular value decomposition, because it naturally separates and uncorrelates the factor vectors of your data. Also, I would like to use this opportunity to introduce to you our software that we've developed, HOTTBOX, which is suitable for multidimensional decompositions and which implements Tensor Ensemble learning. You can check out our GitHub page of the project, documentation, or even play around with the tutorials that we've designed. And these tutorials, they don't even need any kind of installation, and they can be run even on your mobile phones. Thank you for your attention. Any questions?